Sì, 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 sì. Okay.
Hello, everyone. Sorry for the wait. I know it's easy to point your finger to us, and it's the easiest thing, so do that. But actually, this time we had a huge problem with the internet, the university-wide. Not gonna bore you with details. Anyhow, the awesome thing is that the speaker is also the guy who solved everything. So in case we invite you, please be careful that we need you to be also knowledgeable in solving technical problems. So it's a real pleasure to have Luca Mario here, who's going to talk about counting coprime polynomials over finite fields with formal languages and compositions of natural numbers. Take it away. Sorry for the...
Thank you. No problem. No problem at all. Hi, everyone. So, yeah, my name is Luca. I'm quite happy to be back here because actually I was a computer science student in, I think, 2006, 2007. So I did my bachelor, my master, and then my PhD here at Milano-Bicocca. And since I like theoretical computer science, I always came here as well to the math department. So it's always a pleasure to see known faces and new ones. And today I wanted to give you this talk related to work that I actually started during my PhD. So it is already dating back from 7 years ago, I'd say. And now I finally managed, after a long time, to, let's say, wrap it up in a nice paper that is currently under submission. And it's nice because it is something that is both related to algebra, to cryptography, which is one of my main research interests. And also you will see now here that there are some interesting connections with combinatorics and formal language theory, which I don't know if you're already aware about it. This is a topic that is usually explained in computer science courses, but anyway, I will give some very brief concepts just to keep up with what we are going to talk about. So let's start. Maybe I can, I need to stay here or there with the camera. Yeah. Okay, yeah, here. So, of course, I need to focus back here. Yeah, so we start with basic objects that are coprime polynomials over finite fields. In particular, we will deal just with polynomials over the field F2, so just 0 and 1, very simple. So we are going to select, to denote them like this, so pairs of binary coprime polynomials, both of degree n, okay? So it means that they are all monic, these polynomials, because of course we only have 0 and 1 as possible coefficients. And then of course, this will be coprime if their greatest common divisor is equal to 1. And these pairs of coprime polynomials have already nice applications in cryptography and in coding theory, because for instance, in cryptography, you can use them to mount an attack towards the implementation of DFM and key exchange over finite fields using an algorithm by Coppersmith that dates back to the 80s. And also in the decoding of certain error-correcting codes that are called alternate codes. And this is a very broad class of linear codes, including BCH, Reed-Solomon, and many others. So they are interesting as mathematical objects also for a lot of applications in coding theory and crypto. So in order to check if if two polynomials have the greatest common divisor equal to 1, so they are coprime, you run Euclid's algorithm. So quite basic. Here we have a very brief example. So we are going to use the Euclidean division that has this form, and then we apply iteratively over two polynomials that we want to compute the greatest common divisor of. So we start with the first equation, then we go with the second. We are going to use the dividend here. We are going to, it will become sorry, not the dividend. The divisor here will become the dividend, and this will be divided by the remainder of the previous iteration. And then we continue like this until we arrive at a certain point at 0 as a remainder in the Euclidean division. We can also have a more compact notation where we are going to put the relevant pair of polynomials in each iteration. So this is the polynomial that is being divided, and this is the divisor. And then we're going to connect it to the next pair by putting the corresponding quotient over this arrow. And so this will be shifted to the left in the next iteration, and this will be the new divisor. And then we continue like this until we arrive at the end. So in this specific example, these two are not coprime. Why? Because we have like the second to last remainder that is not 1, it's x plus 1. So this particular pair is not coprime. Now, there is like this basic remark that have been, let's say, made by Arthur Benjamin and Charles Bennett, that like this algorithm can, of course, be reversed, right? So if we start from the last pair in Euclid algorithm, and we use the same sequence of quotients, but in reverse order, then we are going to obtain the original pair where we started from, right? We call this, or they call this Diehl-Q's algorithm because it's just Euclid's reversed. So if we do this for the specific pair of this example, then we are going to recover the original pair F and G, okay? And now suppose that we are going to change the last remainder here that was 0, that was indicating that the pair is not coprime, to 1, which means that actually this is going to be coprime now, right? Because we are going to change it as the last remainder equal to 1. And this is by definition the greatest common divisor. If we apply the same sequence of quotients, then by construction, we're going to get a pair, this one specifically, that by construction is coprime. So this is a very basic remark, just switching the last remainder from 0 to 1 and then applying the same quotient in reverse order. Now, this is actually quite useful because there is a very nice bijection that you can make between coprime and non-coprime pairs over the binary field F2. So specifically, you're going to start from a pair, any pair of coprime polynomials of degree n, and then you apply Euclid. Then if this remainder is 0, you change it to 1. And otherwise, if it's the other way around, you're going to set. So if the last remainder is 1, so you want to map like a coprime pair to a non-coprime pair, then you're going to set the last remainder equal to the second to last in order to, let's say, get something that is not coprime. Then you apply Diehl-Q's algorithm in both cases, and then the result will be respectively either coprime or non-coprime pairs. So there is like a one-to-one correspondence between coprime and non-coprime pairs. And this is quite nice because it means that if you're going to take any random pair of degree n, then the probability that it is coprime is exactly 1/2. Or equivalently, if you want to count them, it's 2 to the power of 2n minus 1 by basic combinatorics. Now, we're going to look into some more constrained version of this problem that was what interested me for my PhD. And in particular, we are going to require that the two coprime pairs have the same non-constant zero, non-zero constant term, sorry. So they both need to have a +1 for the, let's say, the coefficient of degree 0. And we want to both count all such pairs that are coprime, so that have this additional constraint, and also this enumeration, find an enumeration algorithm, so a procedure that is able to enumerate them all, generate them all by starting from a single, the degree basically as an input parameter. Of course, the trick that we used before for doing this bijection does not work here anymore, because if you start, for instance, for a pair like this, there is non-coprime, where you have both non-constant zero terms, non-zero constant terms, sorry, I'm continuing to swap the two terms. Then you're going to, if you apply the same trick of using Diehl-Q's algorithm, then you're going to get a coprime pair, which is not of the required format. So it will have, like, in this case, 1 in the first polynomial and 0 in the second, for instance. So it is not a bijection in this case that we are after. And more specifically, why do we want to do this specific complication? Well, this has to do with what I was studying during my PhD. So my PhD was on the applications of cellular automata to cryptography. And at a certain point, I got interested into secret sharing schemes that are related to combinatorial designs, in particular to orthogonal Latin squares. And one of the results that I proved in my thesis was that if you start from, I'm not going into the details of cellular automata because this would go beyond the scope, but if you are interested, I can explain something later in during question times. Anyway, you have some cellular automata that are, let's say, you can consider them as a specific type of linear maps in this case. And since they are linear, then you can associate a polynomial to each of these cellular automata roots. And the nice thing is that these linear cellular automata are going by themselves to construct Latin squares. And these Latin squares will be pairwise orthogonal if and only if their associated polynomials are pairwise coprime. So this is why I got interested in this problem of counting coprime polynomials where both polynomials have the same degree, n, and a non-zero constant term, because in particular, all these polynomials of cellular automata, in order to make singularly Latin square, they need to have like a polynomial with a non-zero constant term. So that's the whole motivation. A little bit more about this is that these objects, orthogonal Latin squares, are related to secret sharing schemes, where you can imagine you have like this protocol where there is a dealer that wants to share a secret information among a set of n players, such that at least k players out of n are required to pool their shares together in order to get back the original secret. On the other hand, all subsets of less than k players are not able to determine anything about the secret. And this has a lot of applications, like in cryptography for digital signatures, for instance, or also secure multi-party computation and other type of cryptographic protocols. The thing is that basically, if you consider a threshold k equal to 2, so at least 2 players are required in order to get back the secret, then actually these are exactly equivalent to families of mutually orthogonal Latin squares. So that's the whole connection, let's say, for an application point of view. Now, in order to, let's say, solve this problem, back in my PhD, it was like second year of my PhD, so already 7 years ago, time flies. And I started like by asking to Arthur Benjamin, so one of the 2 authors of that paper where they were going to explain the bijection between coprime and non-coprime pairs in the general case. And then I asked him, said, okay, what do you think about this complication? Because actually I have no clues about how to solve it. And then he replied to me like half an hour later, saying that, oh, well, off the top of my head, I'd say that there are, if we consider like polynomials over any finite fields, not just binary polynomials, q to the power of q minus 1 equivalence classes, all of which are coprime except 1, but I may be wrong. And my reaction was something like this at the time, because I said, okay, I really have no clue how we managed to came up with this. Moreover, he is kind of an interesting guy. He is one that does like number theory and algebra, but he's also like a magician. So you see him like in a lot of TED Talks, like doing a lot of showing his impressive mental calculation capabilities, and he's quite good at that. So he's kind of a character. So I said, okay, I will just keep this. I will just trust his word on this and try to work my way to see if he's right or not. And actually 1 month later, after busting my ass about trying to prove this, what he was saying, he was indeed right. So I remember that I was feeling like half of my notebook about this problem. So he was right indeed. The problem is that unfortunately this clue was not enough to solve what I was after. So to actually solve the counting problem in this case. And so basically, actually, in order to solve this, I had to think a little bit more through it, have some help from my supervisor, Enrico Formenti, who is like a joint author of the work that we are currently submitting to a journal about this topic. And we were able to, let's say, prove it using a recurrence equation. Now, in the interest of the sake of time, since we were running already a bit late, maybe I will just skip this part of that was supposed to be done on the blackboard, because this would take like quite some time in order to do it. But let's say that it is possible, like to say, if we consider coprime polynomial pairs over the finite field F2, where we have degree n for both polynomials and both of them have non-zero constant terms, then you can solve this counting problem using a classic recurrence equation approach. And the final recurrence is the following one, which has this following closed form. So 4 to the power of n minus 1 divided by 3. Interestingly, this same sequence of integer numbers occurs also in the online encyclopedia of integer sequences, which is maintained by Niels Lowen, and it is like full of possible integer sequences related to the most disparate mathematical problems. And one of my initial strategies in trying to prove this counting result was that, okay, it really seems by doing some simulation that I didn't know that this was the recurrence at the time, but by simulation with computers, I could see that there was exactly this type of sequence showing. So I said, I will try to exploit some of the facts that are known about this integer sequence, because it is related to a lot of interesting mathematical facts, quite different from each other. And then try, okay, I will try with this characterization and then see if it is possible to use it in order to solve my problem as well. One of those, I mean, it's not really useful, but one of the things that it is related to this sequence is that it is quite easy to prove if you start from numbers in this sequence that the Collatz map is going to converge to the periodic sequence 1, 4, 2, etc.
But I mean, the right term is not an integer all the time.
Which
It must be something. If you say, I mean, 4 to the n minus 1 is not always divisible by 3. And moreover, the left term is bigger than the right term. So it looks like your a n minus 1 is negative.
Yeah, actually, you need to consider there is a problem with a small problem with a shift. Actually, if you're going to see it like on the OA's website,
Yeah.
and it's not exactly with this form, but it is, if I remember correctly, 4 to the power of n minus 1 divided by 3. If I remember correctly. In that case, then you can show that it is always integer and you are not going to get negative numbers. The fact that here I have n minus 1 is related to the fact that I wanted to start it from degree that was at least 2, if I remember correctly. So that was the reason why I have an n minus 1 here. If I remember now the details correctly, I'm not exactly.
Yeah, but not, I mean, if you look 4 to the n minus 1 is bigger than 4 to the n minus 1 over 3. So that would mean that your a n minus 1 is negative, which doesn't make much sense. So, I mean, there should something you have to correct there.
Okay, yeah, thanks for the, I cannot see right now the, let's say at a glance this thing, but for sure I will have a look at it. Thanks for
You're welcome.
And yeah, anyway, so this, let's say, was first step in actually showing that this counting problem could be solved at least for binary polynomials. And then we generalized this to any finite field of order Q using another type of recurrence that was more complicated because you need to account for any possible power of a prime. But anyway, you can find then the details of all the proofs for the counting proof in this paper that was published in 2020 by me and other co-authors, including my supervisors at the time. So the problem was that this was just a counting formula and enumeration was not addressed, which was also one of the other two remarks or properties that we wanted to obtain at the end of our investigation, because enumeration is useful from an algorithmic point of view in order to construct Latin squares for cryptographic purposes, for instance. So in order to address the enumeration part now, we are going to, let's say, take another angle at this problem. And this angle is actually to see, okay, we're going to analyze the Euclid's algorithm or Dylke's algorithm equivalently, using, well, by studying the sequence of quotients, such that these quotients are able to only give coprime pairs if we start from the last set of remainders 1 and 0 at the end of Euclid's algorithm. So we can, let's say, decompose this problem in 3 parts. The first part is that we have our sequence of quotients from Q1 up to Qk, let's say. And then each of these polynomials, these quotients will have, let's say, a specific form. So they will have degrees, there is d1, d2 up to dk, for instance. Then we will have the middle terms, and finally the constant terms of these polynomials. So we are going to study them separately, each 3 of them. Now, as a notation, I'm going to say, okay, that the pair Ri and Ri plus 1 is, let's say, are the consecutive remainders that you're going to produce by applying Euclid's algorithm at the ith step, okay? So it means that you can rewrite the Euclidean division equation for step I plus 1 in this way, okay? So you're going to express like the ith remainder in Euclid's algorithm using the, let's say, remainder in step I plus 1, the remainder in step I plus 2, and the quotient in step I plus 1. Why do we need this? Because if we're going to start here from the constant term, then we can exploit this fact in order to characterize the sequence of remainders as what is called like a regular language. So let's start from the basic part. So we have this equation that we said this is going to explain how the remainders are going to be expressed using the next remainders in the iteration of Euclid's algorithm. And as a notation, we are going to say, okay, this pair Ci and Ci plus 1 will be the constant terms respectively of Ri and Ri plus 1. Si plus 1 instead is the constant term of the quotient in step I plus 1. And finally, with this function here, delta of these two arguments, so the pair and Si plus 1, we are going to get as an output the next pair Ci plus 1, Ci plus 2. So the constant terms for the next iteration of Euclid's algorithm. So you can actually feel, let's say, all possible, let's say, combination of values starting from Ci, Ci plus 1, and Si plus 1, and then make some considerations over this equation in order to get what will be the next pair in of the constant terms of the remainders. Sorry. So for instance, if you see, like if you have like constant terms both for the first and the second remainder here, so in step I and I plus 1, and then the next quotient is not going to have a constant term, then by looking here, it must be the case that the next one must have a non-zero constant term, because we are going to shift Ci plus 1 is going to become like Ci. In this case, we are going to shift it to the left using Euclid's algorithm. And then the next one will have non-zero constant term in this case. Why? Well, because if we start from, let's see, so this one that has a constant term, and this one that has a constant term, and this one also has a constant term, okay? So it means that this multiplication here will have a constant term because we are multiplying something that has plus 1 with something that has plus 1. So it must be the case that this one doesn't have the constant term, okay? And so on, so you can feel everything with this type of observations here. So in the end, once you have this type of let's say table here that is going to express all the values of delta of this transition function delta, then you can also write a graph. So it is similar to a finite dynamical system in a sense. This in computer science is also called a finite state automaton, because actually if you're going to consider all possible words or strings of zeros and ones that are produced by a walk over this graph, then you're going to get what is called a regular language, because it is like recognized by this specific type of finite state automaton. So if you start, for instance, from here, this will be the first state, the initial state, because you say that the first two polynomials always have the non-zero constant term. And then if you see that the quotient has a zero constant term, then the next pair will also have in Euclid's algorithm, both of them will have non-zero constant term. On the other hand, if the quotient has 1 as a constant term, then it will be the case that the first polynomial in the next pair will have a constant term, and the other one won't have a constant term, and so on, and then you continue like this. So if you start with this, and then you arrive at the end, and you have like a proper, let's say, sequence of quotients for your specific pair that where both polynomials have a non-zero constant term, then you have like a sequence of constant terms for the quotients. There is part of what is called a language or regular language in formal language theory. So what is like a formal language, or specifically like a regular language? We have, maybe I can write something here on the blackboard. So let's say that we have sigma, that is, let's say, any finite set. And this finite set in this case would be, in our case, 0, 1, so the binary alphabet, okay? And then you're going to construct what is called the monoids over words of this finite alphabet, which is denoted like this, so sigma to the star. And you associate with this set a concatenation operation. So you start from symbols here in this finite set, and you're going to concatenate them in order to get strings or words with them. Okay, so this is called, if you check the properties, this is a monoid. And you say that in general, a language is any subset of sigma star, okay? Now, regular languages are a little bit different in the sense that, or more constrained, so it's not just any subset of this monoid, but they are something that you construct in an inductive way. So you say, okay, the empty word, which is usually denoted as epsilon, and then each of the singletons inside sigma, so 0 and 1, these are regular languages, okay? And then you're going to define 3 possible operations over these sets, okay? So the first one is the union, okay? The union of 2 languages, so let's say L and M, and you say that L, M are regular languages, okay? So the union is still a regular language, okay? The concatenation is also a regular language. And finally, the clean enclosure is also a regular language. Clean enclosure means that we are going to take, let's say, any word inside this language, and then we are going to take either 0 or any number of copies concatenated with themselves of the same word, okay? So this is the way how you're going to, sorry, maybe it's not really formal, but just to give an idea of how regular languages are defined. So it means basically, going back here, that the set of all constant terms for this problem can be defined by a regular language, okay? And if it is defined by a regular language, then we can get a regular expression. So a regular expression is basically a formula that is telling you how to, let's say, generate. So it's like a grammar. You start from the symbols of your alphabet, and then the plus sign is going to be basically the union here of 2 languages. So in this case, you're going to choose either 0 or 1, for example, here. If you have just concatenation, then you're just going to concatenate the 2 symbols or substrings. And then you also have the clean enclosure, which means, like in this case, either 0 or more copies of 0, for instance. So if we go back to our problem, actually the graph that I showed you here in the previous slide, this is related to Euclid's algorithm, okay? But we want to use Dyrkjus algorithm instead. So in order to reconstruct from the bottom of Euclid's algorithm, reconstruct a valid pair in our case, okay? But this is, let's say, simple to get like the inverse automaton in this case, because this, if you look, sorry, if I go back again, if you look at this specific table, then it is permutative in the sense that if you're going to fix, let's say, any state here, then the set of possible outgoing edges from this graph is a permutation of the symbol set, basically, which means in practical, in concrete sense, that you can get the inverse automaton for Dyrkjus algorithm by just inverting the sense of the arrows in the graph. And then we say, okay, the initial state of this automaton will be 1, 0, because this is the case where when you have a coprime pair, so in the end, at the end of Euclid's algorithm, you will have, let's say, a 1 and then a 0 if you iterate one step further, okay? The final state instead is 1, 1, because we want the final pair to be, let's say, composed by 2 polynomials that both have a non-zero constant term, okay? Actually, we can still use 1, 0, because it is quite simple to show that if you start from a pair of this type, so both polynomials have a non-zero constant term, and then you apply Euclid's algorithm in the first iteration, then the first quotient is always 1, okay? Okay, so we can just shorten, let's say, the word by one character, by one symbol. And then we say, okay, this would be both the starting state of our automaton and the final or accepting state. So if we are going to start from here, read a sequence of constant terms for the quotients that is ending back here in the end, then this will be a good sequence for, let's say, constructing like a valid pair where both polynomials have a non-zero constant term. If we get the regular expression of this language, I'm not showing you the details, but it's something that is quite, let's say, basic to do in regular languages. You start from the graph of this finite state automaton, and then you apply like a technique that is called like state elimination, and then in the end you obtained the whole regular expression for this language that is generating words in this language. Now for enumeration, so the idea here is that now we need to enumerate all words of length k, where k is the number of quotients in our sequence of Euclid's or Dilthus algorithm. And for this, there are a lot of algorithms already in the literature that are doing that in an efficient way. For the counting part instead, it's interesting because we can exploit a connection between a regular language theory and algebra, in the sense that there is this famous theorem that was proved by Noam Chomsky and Schutzenberger, which is basically associating to each regular expression a formal power series, okay? And this formal power series is constructed as follows. So if you start with the symbols of your alphabet, 0 and 1 in this case, then to each of them you substitute an unknown, x. Then plus and concatenation in the regular expression maps directly to plus and multiplication in the formal power series. And finally, the clean closure, the star operator, will be mapped to this specific rational function 1 over 1 minus x. Okay, so if you apply this, let's say, transformation here to this specific regular expression that we got from the previous finite state automaton, then you're going to get a formal power series whose generating function is this rational function here. Okay, this is the reason why regular languages sometimes are also called rational languages, because by this Chomsky-Schutzenberger theorem, they are associated to rational functions. There are other types of languages like context-free languages that are broader. It's a broader class than regular languages that are associated to algebraic functions instead. Anyway, if you start from this generating function, then again, I'm not showing you the details of this, but I will give you like the reference of the paper if you are interested later to see it. Then you will get a closed form for the coefficients of this formal power series of this form here. So we can see that we're already kind of in the right direction, because in the end, when we showed like the recurrence equation approach earlier, we had like 1 over 3. So we were dividing everything by 3 when we were counting them, right? And okay, so this is for the part of the constant terms of the sequences. Okay, so the sequences of constant terms of the quotients. Sorry. Now we have the second part, that is the degrees of the quotients instead. So in the case of the degrees of the quotients, then we can characterize them as composition of natural numbers. What does it mean? So suppose that we start from an example. We have n equal to 4, and then we have this sequence of quotients in Dilthus algorithm. Okay, we are going to discard these two here because these will have degree 0. Okay, so we will have degree 1, degree 2, and degree 1 again. And if we apply Dilthus algorithm, then we're going to get a valid coprime pair in the end, because both of them have a non-zero constant term. So the constraint here is that the sum of these degrees, so 1 plus 2 plus 1, must be equal to the starting degrees that you want of your polynomials to end with. So 1 plus 2 plus 1 must be equal to 4. And moreover, you need to have 3 summands, because we said that we have, if we discard the first one and the last one, then this is fixed by the sequence of quotients. So we are interested in seeing what are the combinations of ordered sums of an integer number n, okay? And these are called also compositions of natural numbers. Actually, this is good, because if they were unordered, then these would be partitions of integer numbers, and actually counting partition of integer numbers, as far as I know, it's still an open problem, and it's not been solved completely. Compositions instead are quite easy, because here we are requiring that they satisfy a specific order, the summands, because we can represent them as, suppose that we have n ones, okay, and between them we are going to put n-1 boxes, okay, and then each of these boxes can be filled either with a plus or with a comma. And the example, so if we go back to the example that we were making the earlier slide, sorry, then we would have 1, 2, and 1 in our composition. So we can put like a comma in the first in order to separate two summands, a plus in the second box in order to say, okay, I'm going to sum the two adjacent ones in order to get a 2 in this case, and then get another comma to obtain the last one. So this will map to 1 plus 2 plus 1 if we are going to set n equal to 4, the degree, and the length of the sequence equal to 3 quotients in total. So the next thing is that in the end you can represent this as using a power set lattice. So you start from the bottom of this lattice where you have all plus in these boxes. So 1 plus 1 plus 1 plus 1. And then you construct all the others by using, let's say, the basic, using a specific covariant relations for this specific type of representation. But in the end, you're going to get exactly like a power set lattice that is isomorphic to the set of all subsets, basically, to the set of, to the power set. Yeah. So in particular, in this poset or this lattice, we can remove the top element. So we cannot use a 4 plus 0 in this example. Why? Because you can show that you cannot just jump from the initial pair at the end of Euclid's algorithm directly to the final pair. So you need to do at least 2 steps. This is also related to the fact, if I go back a bit here, is the fact that if you do just one step in this finite state automaton, then you always end up either here or here, and these are not accepting states. So this it can be the case that you are going directly in one in a valid pair in just a single step. So you always need to do at least 2 steps, for instance. Okay. Okay. So we remove the top of this poset, and then we are going to focus on just a single. I don't know how they are called in chains in the poset lingo. So for instance, we said that here we wanted our sequences to be of length 3. So we're going to consider just this chain here of this poset. And okay, it's actually now it becomes easy to both enumerate them, these compositions, and to count them, because in order to enumerate them, what you want to do is just to enumerate all binary strings of length n that have k ones. So you're going to, let's say, associate, for instance, to 0, the plus, and to 1, the comma, okay? And then you say, okay, I want to have a certain number of ones or of commas inside my, my sequence of degrees of quotients. And then I'm going to enumerate them all, and there are several algorithms in order to do that in an efficient way. Counting instead, well, you can use, well, this is really basic combinatorics, counting the numbers of all possible subsets of a specific cardinality is just a binomial coefficient. So in particular, n-1 over k-1. So finally, we come to the third part, and the third part were the middle terms of the quotients of the polynomial, of the quotients in the sequence. And actually, it's, let's say, kind of easy to show, or it's kind of intuitive, that the middle terms are actually independent of everything else. So they can be freely chosen, which means that once you have fixed the length of your quotient sequence, then let's say everything is, let's say, independent. So the middle terms that are freely chosen, the sequence of degrees, and finally the sequence of constant terms. So you have an enumeration algorithm. We are not going into the details of all of this, but basically you're going to do like 3 iterations nested one into each other. Once you have fixed the length of the sequence of the quotients, then you generate first all compositions for the degrees of the the sequence of degrees. Then for each of these sequences, you're going to enumerate all possible constant term sequences using an enumeration algorithm for finite state automaton. And finally, once you have also set the middle terms inside there that can be freely chosen, then you apply Dilthus algorithm from the initial pair 1, 0 over this specific sequence of quotient that you just constructed in this part of the algorithm. For counting, on the other hand, we reobtain this formula here. So 4 to the power of n minus 1 divided by 3, minus maybe some typos that was remarked by a listener before. But anyway, we have this sum from 2 up to n of what? 2 to the power of n minus k, which is the number of possible combinations for the middle terms, okay? Then you have the sequence of degrees, which is the binomial coefficient of n minus 1 over k minus 1. And finally, you have the closed form for the formal power coefficients of the formal power series in the case of the sequence of constant terms, which was this one. And in the end, after doing some calculations, you get again this final closed form, which is, let's say, nice because it's, let's say, an independent confirmation of the fact that the recurrence equation was correct. So coming to an end, to sum up, basically the enumeration is much more complicated, and also the counting part is more complicated when you're considering coprime polynomials, where both polynomials have a non-zero constant term. Instead, when you had like 3 constant terms, you just had this nice bijection by Benjamin and Bennett that was quite easy to use and to work with. And in order to deal with this specific complication, then we divided the problem in 3 parts. So the sequences of constant terms that you solve using regular languages and algebraic language theory with formal power series. Sequences of degrees that are compositions of natural numbers. And finally, sequences of middle terms that are just, let's say, combinations of binary. So the set of all possible binary strings of a specific length, so it's 2 to the power of something. And this basically concludes this, both the enumeration and the counting result part of this problem. And these have been like informally published so far in a preprint that is available on archive. Basically now it's under revision. It has been under revision in cryptography and communication for a very long time because we submitted it like 1 year ago and we just received the revision like 1 month ago or something like that. So it's still a long way to get it finally published. And for future directions, actually what we are interested in is to generalize this type of enumeration strategy to any finite field, because this is just for binary coprime polynomials. And also not just to pairs of coprime polynomials, but also to m-tuples in general of pairwise coprime polynomials. And also to see the applications to cryptography of these results. So Latin squares for secret sharing. Then this type of construction with Latin squares and cellular automata can also be used to construct other type of algebraic objects like Hadamard matrices and bent functions, partial spreads. So there are a lot of connections there. And yeah, that is it. So thank you for your attention. And yeah, if you have any questions, you're welcome to ask them.
Thank you, Luca. Are there questions?
Yeah, just to point out that, I mean, you just needed to switch the exponent in the right-hand side term. I mean, it's just a sum of geometric progression if you think of it. But anyway, I have a curiosity. You showed in the slide 15, I think, is
Go back.
The shape of this A sub k.
15 here.
Yeah, that's right. If I remember correctly, that is also counting the number of code words in the zero-sum code of weight k. Do you see why there is such a relation?
Okay, yeah, this, yeah, it might be There might be some connection for sure. Actually, now I'm not acquainted with what is again the number that you were saying now.
I think you attended my course in coding theory, right?
Yeah, right. Yeah. I followed it, but I didn't give the exam. Actually.
If you remember, I mean, you can take all vectors in a vector space of dimension, say n, and look at the subspace. I mean, the hyperplane where the coefficients just sum to 0.
Yeah.
And then if you would like to count well, say the words, the vectors having weight, Hamming weight equal to k, that's exactly the formula.
Yeah.
So I don't see why there is such a connection with what you described.
With this part here, well, this is just coming from probably, there are some simpler ways to describe it, like you were mentioning now. But this was, let's say, basically just the way that I approached the problem in a certain sense. And yes, since I knew this, like I noticed, okay, I can model this as a particular finite state automaton. Then basically I said, okay, let's see in the literature whether there is a way to enumerate or to count the number of words in a regular language. And there was like the Chomsky-Schutzenberger enumeration theorem that popped up. And then I said, okay, let's go with this. And finally, I mean, we obtained still the same results. So probably there are simpler ways. Well, one simpler way is to use like the recurrence equation that I mentioned before. But for sure, there could be many other connections. Like if you go to this specific, let me see here, the web page for this specific sequence on the online encyclopedia of integer sequence, there is like a lot of facts that are related to this sequence here. So there might be also some links, probably just to, where is it now? Just to this part here, that is, let's say, a factor in this case of this integer sequence. I don't know, it's quite an interesting point that you're making for sure.
Okay, thanks.
Well,
any other question for Luca? At the very end, you said something, but you were fast or
okay.
You said something like this can be used for little functions. I didn't understand.
So they can be used to construct some types of Boolean functions that are used like in coding and cryptography. So bend functions specifically. Bend functions are related to Reed-Muller codes because they're basically the functions that are the farthest possible from the linear function. So where you're just summing input variables. And these are those that have like the highest Hamming distance possible. So you can consider them as those code words that are, well, not code words, those words that are like at the on the surface of a sphere where the center is like a linear function, a linear Boolean function. And then those that are like on this on the edge of this sphere, these are, let's say, maximally possible nonlinear functions. And these are applications in cryptography for stream ciphers, for instance, or block ciphers. Yeah.
When you speak about applications of cryptography, do you think to some specific crypto system or the construction of boxes, you say, from cryptography? So
if I think of the Boolean functions connection, then for sure these are interesting for the design of certain models of stream ciphers, where you have like the combiner models where you're going to mix like, you want to construct like a key stream that is then XORed with your plaintext bit by bit. And then you have like a series of linear feedback shift registers. These are just linear recurring sequences that are generating in parallel the input bits that are fed to a Boolean function. And then this Boolean function needs to have specific properties in order to withstand some attacks. So it needs to be nonlinear, it needs to be balanced. So bend functions are like maximally nonlinear, so they are interesting for one perspective, but unfortunately there is a trade-off because they are not balanced. So they don't have the same number of zeros and ones in their truth table, so they can be used directly. But you can exploit them in order to construct balanced functions that are also highly nonlinear. So yeah, this is one of the possible applications.
Thank you.
More questions? If not, let's thank Luca again.
Thank you. Thanks.
Thank you all for your patience. Now,
So now we can,
yeah.
yeah.